Yo, what's up, guys? Welcome back. Episode 127 today. Yeah, let's take a look. I did upload a video today, this afternoon. I recorded it last night, and I started playing Minecraft for a little bit before I went to bed, and totally forgot to upload it. So I just uploaded it in the afternoon for yesterday. So yeah, recording today's episode right now. But yeah, let's take a look. We got a pincer today. Let's take a look at the sound. There we go. There's our sound. That's only coming out the right side of my headset, dude. That's okay. That's better. Anyway. Okay. Let's take a look at our problem of the day. We got divisible and non-divisible sums difference. Given positive integers n and m, define two integers as follows. Number one, the sum of all integers in the range 1 to n, both inclusive, that are not divisible by m. Number two, the sum of all integers in the range 1 to n, both inclusive, that are divisible by m. Return the integer num1 minus num2. Okay. Num1, the sum of all integers in the range 1 to n, both inclusive, that are not divisible by m. Okay. From 1 to n. Range length. Range 1 to n. Okay. Both inclusive, that are not divisible by m. So if I percent m is equal to 0, we would continue, right? Divisible by m, right? Otherwise, we would do num1 is equal to 0. Num1 equal to I. Right, and now num2, we want the sum of all integers from 1 to n, both inclusive, that are divisible by that are divisible by m. So then we would do num2 for I in range 1 to n. One circle, if I percent m does not equal this one's equal to 0, then we would continue. Divisible by m. Okay. Then we would do num2 plus or equal to I. Then we do res. We would want to return res return num1 minus num2. They keep changing the layout of this, man. Like, let's print I. Okay. N plus 1. Why are we getting... Do we have to return the absolute value or something? My gosh. I don't understand. What am I missing here? But I don't know what I'm missing here. Something's so small. I literally did that. What's wrong with my code? Dude, I don't understand what's wrong. Num2. How am I getting the wrong answer, bro? Reverse the subtraction. No way that works, bro. Like, that's crazy. Okay. Literally says in the problem description to do num1 minus num2, but alright, whatever. Soul Survivor. Let's jump out Leetcode 75, see what we can do here. Right, I think we tried this one, we failed. Let's try this binary search run. You're also given an integer success. A spell and a potion pair is considered successful if the product of their strength is at least success. So I'm trying to figure out how this works. You're also given an integer success. So if the product of their strength is at least success. My two favorite binary search templates. Jade potion. And potions J represents the strength of the jade potion. Okay. Success is 7, right? A spell and a potion pair is considered successful if the product of their strengths is at least success. Got 4 here. 1. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 0 pairs is successful. 0. 3. 1, 2, 3, 4, 5. 3, 6, 9, 12. That's 4, 0, 3 is returned. Honestly, man, if I was given this problem, to be completely honest, I would not know this is a binary search problem at all. Like, 0 chance. Okay. I'm gonna do the brute force way first. Because I feel like doing the brute force way will help me think about hopefully the binary search way, right? Leetcode has a video on this. This is good. Okay. So let's do, okay. Go 45% accept straight. The brute force would be, okay, well, we go for I in range length spells, right? Then we do spell is equal to spells I. For J in range length, no. Potions. Print potion J. Let's print out spell. So we would print 5, right? So that's spell, then we go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. And we would go 1, right? Because 1's the next one, yeah. 1, 2, 3, 4, 5. And then we have 3, yeah. 1, 2, 3, 4, 5. Okay, right? So we would do let's do a res array, right? Let's do, okay. Res dot append. Spell times potions J. We reset res every time. We do code or append. Okay. Then we would do res dot append. We'd append cur. Let's print our res. We make cur equal to this for the next iteration. Okay. Alright. Then we would go through each and check, right? This is definitely, this way, brute force way definitely sucks. For I in range, length, reds, okay. And for J in range length res. Fix this up, right? Yep. Okay. If J is greater than success, let's make a count here. Count is equal to 0, right? Success count plus equal to 1. Okay. Then we would want to do final dot append count. And we would want to return final. Is at least success, so we would need the equals here. Now it's gonna be too slow. Yeah. Okay. We have 2 pointers. How can this be a 2-pointer problem? Let's think about this. I don't understand how this can be solved using binary search. I don't get it. How can this be solved using binary search?
Today you and tomorrow you aren't the same person. If you're tired of what Today You is doing, get an Accounting Fundamentals Certificate from WGU School of Business and get a whole new Tomorrow You in just 6 months. Enroll today at WGU.
Hey everyone, welcome back, and let's write some more Leetcode today. So today let's solve the problem successful pairs of spells and potions. They give us a nice little story, but I always try to ignore those. So we're basically given 2 arrays. One array is of spells, so maybe something like this, and another array potions, maybe something like this. And they're both positive arrays, so we won't have any zeros or negative values in these arrays. which is good because what we're trying to do here is get some value from spells. Well, basically for every single value in spells, we want to know, can we take one of these potions, maybe 2, and multiply it with the spell value? So 5 times 2. And will this result, in this case, which is 10, be less than, or rather greater than or equal to the success value? And this success value is a parameter. It's a single integer value. It's never going to change. So in this example problem, which we have pretty much copied, the success value, the threshold, is 7. So in this case, 10 is greater than or equal to 7. So we do have past that threshold. But we're not just looking for a spell and mapping it to a single potion. We want to know how many potions can we get such that we satisfy this condition. So in this case, the trivial way to solve this problem is...
I just realized when they say at least, right? So technically we can do binary search off... We can run binary search on each value in here at 5, and we can check, okay, well, there's 2 work with 5.
Basically, to go through every single spell, and then for each of them, just cycle through all of the potions and check for each one, do we satisfy that condition where the spell value multiplied the potion is going to be less than, or rather greater than or equal to success. And of course, if we do this for every single value in spells, the overall time complexity is going to be n, where let's say n is the size of spells, and m, where m is size of potions. So we're going to have to iterate through both of them with like a nested for loop. So this is going to be the time complexity. Now, is there a way that we can do better? And if you've never seen this trick before, you might think we can't, or you might struggle to come up with an approach. But I've seen this pattern before, so I know how to tackle it pretty much immediately. And this first example is actually pretty good because they give us a sorted potions array, which kind of further hints to you how to solve this problem. We can take our potions array, and it's not necessarily going to be sorted. It is in this first example, but there are other examples where this array is not necessarily sorted. But that doesn't matter. We can choose to sort this array. Yes, the time complexity will be m log m because m is the size of the potions array. But this is still better than n times m with the nested for loops. And this is actually a lot better, even though it doesn't quite look like it. That's not all though. Once we're done with that, what we want to do is find how many of the potions will work with the spell. Why are we sorting this in the first place? Well, when we immediately saw that 2 does in fact work, do we really need to check any of the values to the right of 2? Because remember, this array is sorted. Why should we check greater values here? If 2 times 5 is greater than 7, then every value to the right over here, which is greater than or equal to 2, is also going to result in a product that is greater than or equal to 7. So there's no point in checking the values here. That's the trick that we use to get this to become a binary search problem, because binary search is a pretty standard algorithm where we have 2 pointers, left and right pointer. We calculate the mid pointer by just taking the halfway point, pretty easy to do. We check an arbitrary value like 3. How do we check it though? How do we know if this is valid? Well, basically 5 times 3 is greater than or equal to 7. Yes, it is. So 3 works. So basically that tells us we don't need to check any of these 2 values to the right. It's not to say that these aren't valid. We know that now all 3 of these values will work with 5. But we're crossing these out because we don't have to check them anymore. We're now going to start doing our binary search on the left side. So I'm going to update these pointers as well. I'm going to cross this out because we don't need to check it either. So we take now our right pointer and set it to mid -1 over here. So right is now going to be over here. We're going to basically do the same thing. Get the mid from these 2. I believe it's going to be this one. And what we're going to find is 1 times 5 is not greater than or equal to 7. So now we found a value that does not work. We're still going to cross it out because we're not going to check this value anymore. But What we're looking for is the point, basically the smallest value that will work. We're basically looking for like the intersection or kind of that pivot point where everything to the right over here, these will work. These potions will work with this spell, but everything over here will not. That's what we're trying to do. And this actually is the point. And at this point, what our binary search would do is say, okay, this is the middle now. We're going to check, does this work? It does. So we basically segregate the values. These ones don't work. These ones do. How many are over here? Well, we can count that without having to look at every single one. We can count it just by taking this last index that does work and basically taking the length and subtracting this value, because we know arrays are 0 indexed. This starts at 0. This is 1. So when we take the length of the array, we get 5. We now want to subtract all the values to the left side of this line. There's just a single 1 over here. And since this is a 0 indexed array, if the mid value is 1, we know there's 1 value to the left of it. If the mid value is 2, we know that there's 2 values to the left of it. So just basic math here. Now we know how to get the count for each value. For each spell, now we know how to get the count of the potions. Once we can do that, all we really have to do is build the output array, which is basically to take every value here and map it to some value in the output, which, well, the value itself is going to be the count. So 4 for this guy, and how many values will work for 1? Well, we would run the binary search again, and what we'd find is that none of these values, even the maximum value, 5 times 1, is going to be greater than or equal to 7, so we'd get a 0 for 1. And for 3, I'm just going to look at the solution here. Looks like we get 3. The reason probably is because these 3 multiplied with 3 are greater than 7, but these 2 are less than 7 when you multiply them. So that's the result. What about the time complexity? Well, there's 2 main factors here. One, we know we had to sort this array at the beginning. We said the length is m, so the time complexity of that is going to be m log m. But there's another thing here. For every single one of these guys, we're running a binary search on this array. To run binary search on an array is just log m, where m is the size of that array. How many times are we doing it? For each value in the spells array. There are n of those. So we say the overall time complexity is n times log m plus m times log m. Or you could even kind of do some cool, well, not super cool, but interesting math like this, but that's not really too important. But with all that said, let's go ahead and code this up now. So to code this, we know.
I think we can do this by ourselves. My brute force method, dude. I'm so sad to leave it, dude. Brute force. Okay. Get rid of the brute force. Okay, so. So let's do, okay, for I in ranged length spells, right? Let's do binary search on, we call binary search, right? Call binary search on, let's do I, nums I. I don't know which one we're gonna need for now, but let's do def binary search. Okay, we want to pass in our I and our nums, our I, and our value, right? Our binary search starts off by creating our left and right, right? So left is equal to 0 and right is equal to the length of spells minus 1, okay? Then we do, well, while left is less than right, okay? Less than or equal to, right? Let's do the same. Okay. We want to calculate our mid. Mid is equal to right plus left divided by 2. it's the same thing. Okay. So then we do, okay, well. Left is less than or equal to right. Really, technically, I don't really feel like we need any of these in a way. Well, actually, maybe we'll need both. If spells mid, not spells, if potions mid, I think this should be potions actually. If potions mid, times by success potions mid times by success is greater than success. And we found it, right? What I don't know is how we run the binary search on this. That's what I don't get. Oh shit, I forgot we have to sort, dude. My bad. Obviously, yeah, we need a result too. So res is equal to this. We try to find smaller index, right? So we would make our right is equal to mid minus 1. Else left is equal to mid plus 1. It's too small. Value. And then we do result dot append. Result dot append s, and we would just return result, right? But here we'd want to return the length of spells minus left is now the first index word potion. I actually don't know what's wrong here, dude. We have a left, we have a... Spells, whoops, meant potions. Stupid errors, man. Okay, I want to finish here.
Now, the first thing we want to do is, and then do, well, it's initially just, I'm just going to binary search at the left, get on potion. Have a left pointer, which is going to be less than, we stop our binary search. But remember what we're trying to do with this binary search. It's a little bit different than like a standard binary search. So I'll try to walk through it. We know we are going to need the middle index. So that's pretty easy. Left plus right divided by 2, even though this can possibly overflow. Usually for coding interviews, it doesn't matter. In a lot of my other videos, I kind of show you how to write this without having it overflow, but I'll skip that for now. Next, we want to check the conditions. What is the condition in this case? Well, this particular spell, we already have that with S, right? This particular spell multiplied by some potion. Which potion at which index? Well, remember, that's why we're running binary search. Our mid index, we want the potion from that index. Is this value greater than or equal to that success parameter that was passed to us? If it is, then this is valid. Else, it's not valid. What about the third case though? What about if this is actually equal to success? It's exactly equal. Usually in binary search, we immediately stop in that case. But here, we actually don't want to do that. Because think of a case like this, where our spell is maybe 5 and our potions array looks something like this, 1, 2, 2, 2, 2, and maybe 4. And our success value is actually exactly equal to 10. Then to start our binary search, what we would do is say 5 times the mid value here. Let's say this is the mid value. So we'd say 5 times 2 is 10. It's exactly equal to the success threshold. So does that mean that we're done with our binary search? No, because even though we found this value, it's actually not the leftmost value. We want this guy over here. Not the 1, but this 2. So since we could possibly have duplicates like this, that's why I'm going to be writing the binary search as follows. I'm going to say, if we get to a point like this, for example, over here, we now want to start searching to the left. We can do that by taking our right pointer and setting it to mid -1. But we also want to save this index. We want to save it in a variable, let's say, which is initially going to be called index. What this should do is find the weakest position, or rather weakest potion that works. And when we say weakest, we mean furthest to the left. So with this variation, that will work. Well, once we add this line here, index is equal to the mid value if it was valid, and then we go further to the left. We just keep going as far to the left as we possibly can until maybe we encounter an invalid value, and then we would try shifting to the right a bit, or maybe we would just stop. When we do encounter an invalid value, we just need to update the left pointer to be mid +1. We're going to start searching to
Okay. Let's submit. Cool. Oh, it wasn't too bad. Let's jump into a ooh. In cost climate says you give an integer. What is this, DP? I think. Yeah. Step on a staircase. From 102 problems, baby. Let's go. Okay, you give an integer array cost for cost I is the cost of the ith step on a staircase. Once you pay the cost, you can either climb 1 or 2 steps. You can either start from step. Okay. OCD.dp, right? Well, if I is greater than or equal to the length of cost, then we would want to just return our count, right? Okay, well, if how's the DP gonna hold here? It's gonna be, the key's gonna be well, we could add differently every time. That's the issue. Where our submissions here, April 28, 2025. So about a month ago. Um, this is outside of our loop, so we would do, well, if I in DP return DPI DPG, right? Otherwise DPI is equal to man, it's too hard to do this thinking about DP. I'm just gonna do it without, right? If I had without, right, I'd have my count here. Okay. I'd have, well, if I is greater than or equal to the length of cost, I would return my count. Alright. I'd reference non-local count here. And I'd loop through and I'd check, okay, well, otherwise I'd return, backtrack, I plus 1 or count plus backtrack I plus 1 backtrack I plus 2. Maybe we should probably put count in here, dude. Right. Then we would return. We have to call backtrack I 0 count 0. Real count. The min of, so real count is equal to min of real count and our count. Non-local real count. Count plus cost I. Let's return our real count. Float inf. Ah, man, these freaking backtracking problems, dude. Backtrack I plus 2 count plus cost I. We would need to start backtrack at 1, start at 0. Okay, there we go. One submit because we need DP, right? Okay, so now to add DP to this, okay, so to add DP, we'd have to go, well, if I, oh shit. Soul Survivor. Okay, let's do our DPI. We can get rid of our real count. We can get rid of our non-local here. So we do the same, but this time we would return 0. Okay, return 0, right? We need to check if it's in, if I in DP, we would return DPI, right? Otherwise we'd compute, right? DPI is equal to cost I plus the min of backtrack I plus 1 backtrack I plus 2. Alright, and then we would return DPI. To call backtrack. Would we start at 0, 0? Start from step 1 or step 2? The DP is always so confusing, man. Sometimes, like, it's so hard to think about the way to do it. Alright, let's take a look at. We did look at house robbers, so let's take a look at that one again. I will be 2 seconds though. I gotta quickly put this in the sink. 1 second. Ooh. Let's jump into another problem. Gone for about an hour now, so let's jump in and take a look at this one again. A house robber, a classic problem. Anyway, professional house robber planning to rob houses along each street. Each house has a certain amount of money stashed. The only constraint stopping you from robbing each of them is that the adjacent houses have security systems connected and they will automatically contact the police if 2 adjacent houses are broken into on the same night. Give it an integer array nums representing the amount of money of each house. Return the maximum amount of money you can rob tonight without alerting the police. Okay. So my first intuition of this problem here is that I think we're going to have to start from here and go here, right? Start here and go here, right? Because there's no way we can both start here, come here, because we can't rob adjacent houses, right? Man, I am sleepy as hell. Okay. Def backtrack. Probably want I, right? Okay. Probably want to do, well, return, we want the min of backtrack I 0 backtrack 1, right? If I is greater than or equal to the length of nums, okay? I want to probably just return 0, right? Otherwise, I'm gonna check, well, if I in dp, then we would return dp I, okay? Otherwise, we want to do, well, dp I is equal to backtrack. Can't rob adjacent houses, right? So we'd have to go I plus 1, I plus 2, right? So I plus 2, okay? We want the maximum amount of money, right? The total amount you can rob. Backtrack 0, 1. Equal to count, sorry. What is it called? Nums I plus backtrack I plus 2. We would return DPI. Backtrack 0, backtrack 1. 10. I feel like I'm missing something, dude. Am I missing something? Right, we're doing the min. We want the max. That's what I was missing. I couldn't remember, bro. There we go. Oh, 3, 4. 0, backtrack 1. Oh, am I missing? Times 0 DPI. We want the max of either Rob or Skip. Turn DPI. Doesn't really say that you can skip here in the constraints. We probably don't even need this max here, it's just making it slower. I'm Soul Survivor. Yeah. On the back. We're pumping through these problems, dude. How many we got? We're at 60 now. Got 15 left. Domino, tromino, tiling. Bit manipulation. This was a problem of the day a little bit ago. I swear it was, like, maybe not. Definitely not medium. Okay, you have two types of tiles, a 2x1 domino shape and a tromino shape. You may rotate these shapes. Given an integer n, return the number of ways to tile a 2x n board. Since the answer may be very large, return a modulo 10 to the power of +7. In a tiling, every square must be covered by a tile. Two tilings are different if and only if there are two four-directionally adjacent cells on the board, such that exactly one of the tilings has both squares occupied by a tile. Yeah, I'm not sure about the intuition of this problem. I don't really get any intuition, so I'm gonna take a look at. There's no Leetcode, man. Damn, bro.
You can find this problem on Leetcode with the ID domino and tromino tiling. I recommend you pause this video and attempt the problem before I reveal the solution. Remember that practice is the best way for you to get better. If you do get stuck, I have two hints that might to fully tile the board. We must make sure that there are no gaps anywhere on the board as we tile the grid from left to right. The first and the last boards on this slide are fully tiled, but we missed a spot in the middle grid, which we never want to do. In many ways, the necessity to have a fully tiled grid is an indication that our DP state should in some way capture a board partially filled up to some position without any gaps. The two boards with the green arrows show boards which are completely filled with tiles from left to right up to a certain position. This is what we want to track. Notice that the last board on the right is tiled out of order. We don't want to do that. Tiling from left to right is generally the way to go. Apart from observing that our grids should be tiled without gaps and tiled from left to right, you should also see that for every column slice, there can be at most 4 possible configurations. Either we're going to have what I call state 0, where neither row is tiled, state 1, where the top row is tiled, state 2, where the bottom row is tiled, or state 3, where both rows are tiled. With that, we have enough information to track all partially filled states up to a certain index. We can conclude that we only need two pieces of information. First is index I, the position up to which the board is fully tiled without gaps. And second, which of the four column states below is present at the rightmost extremity of the current state. I want to note that a pairing of index I and the column state is meant to represent the number of ways to tile the board up to that state. It doesn't represent the tiling of a particular arrangement of dominoes and trominos in any way. This is contradictory to what you might think that the drawings below are trying to imply. Remember that the goal is to count the total number of ways to tile the grid. Let's have a look at some examples of partial states. On the left is the partial state at I equals 1 with column state 0, meaning no tiles are filled in the current column. Beside this is the partial state with I equals 3 and the column state 1, since only the top row is filled, followed by the partial state at I equals 2 with only the bottom row filled, and lastly is the partial state with I equals 3 and a full column state. You might have noticed by now that state 1 and state 2 are symmetric, and that state 0 at position I plus 1 is equal to state 3 at column position I. So there's definitely some opportunity to save space and perform some kind of optimization, but that's not going to matter for this problem because the constraints are so small. Now that we understand how we are representing our partial states, how do we transition from one partial state to another partial state? Unsurprisingly, it's by placing dominoes and trominos. However, as we do so, we need to make sure that we don't leave any gaps as we place blocks. In the example on this slide, the top and the bottom transitions are good, but the middle transition leaves a gap in the grid, which we do not want. When placing the next block, because of the shape of our dominoes and trominos, there are only 4 tiles on the extremity of the state that we ever end up filling. I'm going to refer to these tiles as T1, T2, T3, and T4 as the frontier. The frontier simply consists of the board. Let's have a look at some pseudocode. Don't be intimidated by the looks of the code, it's actually quite simple. I'll walk you through it. First, I define a few variables in the outer scope. The first is the mod value, which is 1,000,007. After the mod, there is n, the length of the board to tile. This is given as input. And after that, there's the DP table, which has n plus 1 rows and 4 columns for each of our column states. Assume that the table is initially filled with null values. Next up is the solve function, which is basically a wrapper function for calling f, the recursive function that does all the work. F itself takes 3 pieces of information. First, I, the index responsible for tracking how far along we've tiled the board. The goal is to find the number of complete tilings for a board of size n. Additionally, f also takes t1 and t2 as arguments, which are Boolean values which represent if tiles t1 and t2.
Okay, this explanation is garbage. Anyway, let's see if AI can help me with it. Domino and tromino tiling. Having primary approach. Oh. DPN. K and Mimo. Dominoes covers 2 squares, 1 times 2, 2 times 1. Dominoes L-shaped 3 squares. You must count how many ways to tile the board completely. Return the number of ways to tile 2 times n board using only full coverage. Result must be modulo 10 to the 9 plus 7. Okay. Think recursively, DP. Ask yourself, if I've sold this for a small board like 2 times K, how can I use it to build up to 2 times n? We'll define. Okay. One valid way. But some of this comes from a formula that works. Man, this is such a confusing problem, bro. Like, dude. Domino, Tromino, tiling, Leetcode. Surprised Leetcode never did a video on this. Like, mod is equal to 10 times left dp k. If k is equal to 0, we will return 1. I understand this part, right? The base case is here. Okay, if this is the size, then if k is equal to 2, we return 2 because we have 2 different ways we can do it, right? So, well, if k in MIMO, just want to return dpk. I guess let's do dp. So use the coordinate dp. Then we have our recurrence relation, right, which is be our dpk is equal to 2 times dp k minus 1 plus dp k minus 1 plus dp k minus 3 dp k minus 3 percent mod return dpk. I just want to study the solution, bro. Like maybe shoot me to the max. Yeah, this is a tough problem, man. I'm gonna call it here for today. You know, maybe it'll come back to me in the future. I don't know, man. This is a tough problem for me to think about, and I'm actually really exhausted. So I'm gonna lie down for a bit. Appreciate you guys watching today, and I will see you tomorrow. Oh.